So what we've talked about so far is a process whereby we would approach a target position and not really care about the final orientation. But now let's bring in a final orientation and say we do care what direction we're facing when we get to our target. The first version of control we'll talk about is a bit of a special case for differential drive robots. And it's by far the version of control you should use for differential drive robots, unless you have a very good reason not to. And the reasons for that is it's going to be the optimal distance traveled, simplest, and a lot of times it'll be the quickest, but not necessarily always. This is not something you could do with Ackerman steering, which is what your car uses, or many other types of robotics. But it is probably what you may have been yelling at your screen in the previous slides. You will just rotate to your target. Go straight forward. And then rotate to your goal orientation. And I don't know why I've switched to using target instead of goal for this slide, so sorry for that confusion. So, first step, rotate to point directly at your target location. Next step, travel directly to your target location. Third step, rotate in place so that you're at your correct position. The rotating in place doesn't quite work on my iPad here because it's not going to rotate around my actual robot's pivot point. It's going to rotate around the center of whatever box I define around it. So that's likely what we'll end up doing. The only downside to this, or downsides I guess, is it's no longer a one stage or one phase control. So unlike what we had before, if you were to implement these two equations, you would, from the beginning of your saying go to the end, always going to be executing that exact same control loop. You're always just setting VR and VL. Whereas here, you'll first have stage 1, where you'll rotate in place. Then you'll have stage 2, where you drive directly forward. And then stage 3, where you will rotate in place again. So that means you'll have to have code for doing those 3 different stages. It's not all done at once. However, you're going to have a lot easier time figuring out nice values for KO and KP. You don't have to worry about how big of a curved path are you taking to your goal. Something that's in between these two is to define a path that goes through what's called a goal point, an intermediate point, and helps you end up at your target location at the correct orientation. So if you were to take our first version here and have this example, you'd likely end up just driving straight ahead and ending up at the target point. And then for the second version here, where we have the 3-step or 3-phase control, you would drive directly toward it and then rotate into place. For this one, you'll have the nice smooth characteristics that we had before. It'll still be a 2-phase control, but essentially what you'll do is you'll pick some radius and define an intermediate point. Such that your controller will drive to that intermediate point, and then given this radius here, you know that it's within your robot's ability to level out and be pointing at the correct orientation by the time you get to your final goal point here. I should say goal pose, since it takes into account both position and orientation. So for this one, your control law will have two phases. Navigate to intermediate point, and then navigate to goal point. The nice thing about this version is that both of those controllers are going to be the same. It's not different in that one of them is pure rotation and one of them is pure translation. Instead, it'll be some sweeping path, sort of like this. And again, this distance here is parameterized by R, which has to do with how tight do you want to turn. So for tighter turns, we could have a closer intermediate point. For wider sweeping turns, we could have a further out control point. And for future study, I'll give you two more here that I think are worthwhile to pick up if you get into robotics. The first is the arcs and line segments control pattern, which will give you optimal distance traveled. And what you do for this is, from your target, you define a circle where the target orientation is tangent to the circle. So in this case, it would look something like this, where our target orientation is a tangent on this circle. You also define a circle of the same radius where your current heading is a tangent on the circle. And finally, you connect the two circles by their closest points. And finally, your path is given by traveling around the arc, the first arc, on a straight line, and then around the second arc. And you're guaranteed to have a minimum distance, so an optimal distance traveled. The radius of these circles, I'll call R, R is defined by the minimum, or the smallest desired turning radius. And so for our differential drive robot, R, so this actually is optimal for our differential drive robot. It just devolves to our version of control without any curvature. Essentially, the radius you're drawing out is 0, and you'll just pivot in place and drive directly to your target and pivot in place again. The final version of control I'll give you is a sequence of points. You could also consider this a path, so instead of just having a arc that you're defining, or having our circles, or doing our rotate in place, go straight and then rotate again, here you're actually going to define a sequence of points. You can do this manually or automatically, and the sequence of points is usually optimal with respect to some considerations, so designed to some sort of specification. And I'll say that means designed to your use case. And the final slide for this lecture I'd like to separate as a separate video, but I think it would be just like a 1 or 2 minute video, so I think I'll just add it here to the end of this one. Your goal for this week is, for the first part of your exercise, is to simulate our control to a goal position. So we won't worry about orientation. Instead, it's really these two equations you're going to worry about. And so I'll put those here as a reminder that this is what you're doing. As I mentioned before, your simulation is used It's used to get a good feel for the control parameters. So what values are actually going to let you hit your target? Because for certain values of KO and KP, you'll just never be able to reach your target. So for example, if KO is too small, you'll never be able to orient toward the target. Or if KP is too large, you'll continually overshoot and not be able to settle down near enough to your target. Now, clearly this isn't going to be as simple as your code, but essentially what you'll do is for time t in your range of time, and we'll say you'll simulate for 20 seconds, and if you don't reach the target within 20 seconds, it'll be done. What you'll do is you'll compute a new pose based on kinematics, and as a reminder, your kinematics is really based on VR and VL. That's how you propagate forward through time. And then you'll compute new values for VL and VR based on your control law, which depends on your current pose. And that's essentially what the simulation will do, is these two equations will update each other based on their current values, and you'll just do that for 20 seconds. The idea being that if you start at some location, your VR and VL might start out to be 0, and you'll have a current pose. And then your control law, given your current pose, will compute the appropriate values for VL and VR, depending on values of V and theta dot for both equations. Then your new values for VL and VR get put into your kinematics equation, and I should really emphasize that this is forward kinematics, so that you can update and get a new pose. So that'll be your assignment for the first part of this week.